This is video 2.6.1, and the objective for this video is to be able to find restrictions on the domain and vertical asymptotes for rational functions. We're also going to start to see some notation here that's going to be important when you get into calculus and when you're trying to find limits. And so pay close attention to that. You're going to be reusing that in the future. Rational functions. So a rational function, first of all, a rational function stems from the word rational, of course. And it's a function that is a ratio of two polynomials. Okay, so any polynomials, so notice the three functions that we have here. The top is a polynomial and the bottom is a polynomial. So we're working with a ratio between two polynomials for all three of these. So that's the definition of a rational function that we're going to be working with. Now the question is asking me, find the domain. So there's something interesting with rational functions, and that is the domain has restrictions. And we're going to be looking at those restrictions and why they happen. So remember, the one thing in the world that you cannot divide by is 0. So we always ask ourselves, when we're looking at restrictions in the domain, we ask ourselves, when is the denominator 0? So in this case, we're asking, when is x minus 3 0? And the answer to that question is when x is 3. So the restriction on the domain for f of x is when x equals 3, it cannot be 3. So we say x can be all numbers except 3. Okay? So it's all real numbers except 3. That's the restriction on the domain for f of x. Now g of x has multiple cases. So we see x squared minus 9. When is that 0? Well, we can solve this in two ways. We can factor the denominator, which is going to be the more common strategy. And we can ask the question, when is this 0? Well, that's 0 when x equals 3 or negative 3. So the restriction on the domain for g of x is all real numbers except 3 or negative 3. So that's our restriction on our domain. Taking a look at h of x, we look at the denominator, it's still a rational function, and we look at the denominator and we ask the question, when is that 0? So when is x squared plus 9 equal to 0? Well, that's, of course, the other way we could have solved this one down here is a similar fashion to this, solving for x squared. But when we square root both sides, x squared is only 0. X squared is only negative 9 if x is an imaginary number. So this will never be 0 for all real numbers. So therefore, x can be all real numbers for h of x. So you may not always have a restriction on the domain, but you will often have a restriction on the domain. So we want to keep an eye out for that. So now we're going to take a look at these three functions again. We're going to take a look at kind of their graphs and what happens at 3. Okay, and what happens at 3 or negative 3? And once again, is there anything interesting happening here even though there was no restrictions? So we're going to take a look at those situations in the coming slides here. So the next thing that we want to understand is this idea of this arrow notation. So we're looking at this function 1 over x. You've seen this function before. And remember, a vertical asymptote is when you have a restriction on the fact that it will never cross 0. Okay, so f of x will never be 0. So think about this. Why can't this ever be 0? Well, 1 divided by any number will never be 0. But we will get really close to 0. So this arrow notation that we're talking about here is we ask the question, okay, what happens to f of x as x approaches 0? What happens to f of x as x approaches 0? Well, the problem is there are two things happening. Number one, f of x is going down to negative infinity as x approaches 0 from the left. But x approaching 0 from the right, if we're coming from the positive end, we see that the function is shooting off to positive infinity. So the way we describe this is we say that as x approaches 0 from the left, from the negative side, f of x approaches negative infinity. So that's how we're going to describe this situation. So we're trying to describe what's happening at these asymptotes. So this is one description we can write. And to write it in a slightly shorter hand, the next one we can write as x approaches 0 from the right. So we talk about right with the plus sign. F of x approaches, let's see, so from 0 from the right, f of x approaches positive infinity. And you don't need the plus sign on the infinity, I just wanted to make it clear that we are going to talk about infinity or negative infinity like we saw before. But notice there's two other points where f of x varies. So we see that f of x also gets really close to 0 as the function gets really large. So the next thing we're going to say is as x approaches infinity, f of x approaches 0. So f of x is getting extremely close to 0. And then we see this direction. Well, what's happening is x gets infinitely larger in the negative direction. So more and more negative, more and more in the whole. So what happens as x approaches negative infinity? Well, we see the same thing as above. We see f of x approaching 0. Those are going to be important descriptions for just talking about real life problems. What's happening as we get really close to this, where are we going to run into? And that's what we'll see when we talk about limits when we look at calculus and when you see it next year in calculus. So that's the arrow notation. So the next problems are partially your checkpoint. So here it is again, another description of it and what's happening here. And the arrow notation if you want some notes. So you can write these down if you'd like, but it's just describing what's happening. You're going to describe in arrow notations what's happening as x approaches an asymptote from the left and from the right, and you'll describe what happens as x approaches infinity and negative infinity, because these rational functions will often have different results as you're approaching those values. So now we're going to take a look at vertical asymptotes. So when we have vertical asymptotes, we're talking about, remember, these lines that they get really close to. Okay, so your assignment for 2.6a will talk about, have you looking for vertical asymptotes. So here's the steps. Number 1, factor and simplify. And then number 2, any number that makes the denominator 0 after you simplify will be a vertical asymptote. Okay, so that's after you simplify. It will be a vertical asymptote, and we'll describe that asymptote as a function that is, well, not as a function, but as a rule, where is x? What does x have to be to have that vertical asymptote? But there's an interesting case that if the denominator cancels with the top, but it originally made the denominator 0, meaning it caused our domain to not be defined there, then it will cause a hole in the graph. So let's take a look to make sense of this and to help us understand what this is saying. So we have these questions. We're going back to the original examples. So we factor and simplify. So I'm going to take f of x and I'm going to write it in factored form. So I take a look here and I don't see really much anything happening. I don't see any simplifying that I can do. So what that means is these two values that make f of x 0 in the denominator, 3 and negative 3, will be vertical asymptotes. So I would start my graph, if I were graphing these, I would have a vertical asymptote at negative 3, and I would have a vertical asymptote at 3. Because those are the 2 points that made my function undefined. Now I'm not sure what happens between here yet, we'll look at that in the future. But I do know that there's going to be asymptotes at that point. How about this next one? This next one's going to be a little bit different. So I have x plus 3 over x minus 3 times x plus 3. So this one, once again, the way to make the denominator 0 are 3 and negative 3. So those are going to be undefined. Those cannot be possible values for x. The domain is restricted there. But I want to see that I cancel these two. So what that means is that at negative 3, there's actually going to be a hole. It's not going to be undefined, it's going to have a hole. It's not going to be an asymptote. So instead of an asymptote at negative 3, wherever the function is, there'll be a hole. So I'd have to figure out what happens as we get really close to negative 3. And I'd have to put a hole in my graph. And we'll show you what that looks like when we start graphing. But we want to be able to locate the vertical asymptotes. So this one would only have a vertical asymptote at 3 because the negative 3 canceled. This one, this final one, will have no vertical asymptotes. Because remember, there's nothing that can make the denominator 0. So we'll have no vertical asymptotes. Here are the graphs that we're talking about for these three functions. So this is the graph of x over x squared minus 9. We'll talk about how to get this graph later, but you can see your two vertical asymptotes and interesting things happening at them. But the next function that has just a slight change to it has a very different result. It has a hole right here. Okay, there's a hole in the graph at that point. It doesn't have a vertical asymptote, and it seemingly looks seamless, but there is a hole, and we will have to represent that with an open circle to represent that hole. And we still have that vertical asymptote. The final graph, h of x, x plus 3 over x squared plus 9, has no vertical asymptotes. So remember that it just is going to have interesting features because of the fact that you're dividing two things, but it will not have any vertical asymptotes. And we'll look at if there's any horizontal asymptotes in the near future. Here's your checkpoints for this video. Your goal is to describe the domain and locate any vertical asymptotes for the rational function. So remember the two steps. To factor, that'll help you decide what makes the denominator 0, and then to simplify. And if you can simplify something and it cancels, remember you're looking for holes and asymptotes. So if you can find any holes that are restricted on the domain, that's just as important. And we'll be using those things to graph them in the near future. So bring in your questions and concerns to class.